Let's talk now for SN1 reaction. SN1 reaction stands for substitution nucleophilic unimolecular. This means that the reaction is a first-order process and it depends only on the concentration of alkyl halide. The concentration of the nucleophile does not appear on the rate of the equation. An SN1 reaction takes place by losing the leaving group before the nucleophile approaches. Let's take a look at this scheme on iPad. As you can see here, the rate of the reaction depends only on the concentration of the alkyl halide. The nucleophile is not present. As for the mechanism, as you can see here, the rate determining step is the speed at which the leaving group goes away, in this case the chlorine minus. The step at which the nucleophile bonds to the carbocation intermediate is a fast step. The step with the highest transition state energy is the rate limiting step or the rate determining step. No reaction can proceed faster than the rate limiting step. This acts like a traffic jam or a bottleneck. As you can see here from this graph, here is the energy. The step at which the leaving group goes away, or the alkyl halide, requires the highest energy. The second step at which the nucleophile attached to the carbocation is a fast step. Because the SN1 reaction occurs through a carbocation intermediate, its stereochemical outcome is different from the SN2 reaction. Carbocations, as we have seen, are planar, sp2 hybridized, and achiral. Thus, we can carry out SN1 reaction on one enantiomer of the chiral reactant and go through an achiral carbocation intermediate. The product must lose its optical activity. That is, that symmetrically intermediate carbocation can react with a nucleophile equally, while on either side, leading to racemic mixtures of enantiomers. But is this true? In fact, few SN1 displacement occur with complete racemization. Most of them give a minor 0 to 20% excess of inversion. This lack of complete racemization in SN1 reaction is due to the fact that ion pairs are involved. But what this means? First proposed by Samuel Weinstein at UCLA, dissociation of substrate occurs to a given structure in which the two ions are still loosely associated, in which the carbocation is effectively shielded from reaction on one side by the departing anion. If a certain amount of substitution occurs before the two ions fully diffuse apart, then the net inversion of configuration will be observed. As you can see here, this side is open to attack, but this side is shielded from attack at the beginning due to the anion or the leaving group. And this is the effect of ion pair. And we see an excess of the inversion on one side rather than on the other side. That's why we do not have a complete racemization. Okay? According to Hammond Postulate, the factors that stabilize the high energy intermediate also stabilize the transition state, leading to that intermediate. Since the rate limiting step in SN1 reaction is a spontaneous unimolecular dissociation of the substrate to yield the carbocation, the reaction is favored whenever a stabilized carbocation intermediate is formed. The more stable the carbocation intermediate translates to a lower transition state energy and a faster SN1 reaction. The stability order of carbocations proceeds as follows. Tertiary carbocations are more stable. Secondary comes next, and after that comes the benzylic and allylic carbocations that are almost as stable as secondary carbocations. The reason behind this is that they have the possibility to make resonance structures and to be more stabilized. Okay? In terms of groups, reactivity, of course, tertiary and secondary are the best for SN1 reactions. But also allylic and benzylic give SN1 reaction. Something to note here that allylic and benzylic can go also an SN2 reaction. But this is a topic that I will discuss in a future video. What about the leaving group? We said during the discussion of SN2 reactivity that the best leaving group are those that are most stable. This is those that are conjugated base of strong acids. An identical reactivity order is found for SN1 reactions. Because the leaving group is directly involved in the rate limiting step, thus the SN1 reactivity order is this. The same as for the SN2. Tosylate, iodine, bromine, chlorine. You note here that you have also water. This is because SN1 reaction, which is often carried out under acidic condition, neutral water is sometimes the leaving group. We will see an example here. As you can see here, tertiary alcohol react with hydrochloric acid, and you can see the leaving group is water here, okay? Or protonation of the hydroxy group here, and after that this goes away and the nucleophile attack here, and you have the formation of alkyl halide, and also the leaving group is water, okay? What about the nucleophile? Because the SN1 reaction occurs through a rate-limiting step in which the added nucleophile has no part, the nucleophile can't affect the rate of the reaction. Neutral nucleophiles are as effective as negatively charged ones for SN1 reactions that are frequently carried out under acidic condition. What about the solvent? The property of the solvent that contributes to ability to stabilize the ion by solvation are related to the solvent polarity. As you can see here, polar solvents such as water, methanol or ethanol stabilize the carbocation intermediate. Stabilization of the carbocation intermediate translates to a lower transition state energy, so a faster SN1 reaction. Let's move now to comprehension. Take a look at the point A. Is that reaction an SN1 reaction? As you can see here, the substrate is a secondary benzylic halide, okay, because it's a benzylic here. You have a polar solvent, such as a mixture of ethanol and water. You have a poorly negative nucleophile, so it fits perfectly the condition of an SN1 reaction. So this is SN1 mechanism. What about the second one? Here we have an allylic alcohol that is a secondary alcohol, and it is in a protic solvent such as methanol and carried out under acidic condition. So also this one fits perfectly the condition of SN1 reactions. So also this one is SN1 reaction, or goes through SN1 mechanism. Okay? Thank you so much for watching, and look forward to see you in the next video. Peace.